Hello, everyone. I am pleased to have the opportunity to introduce NARI's neutron diffraction instrument design to all of you. Our neutron science team is listed in the presentation and is divided into three parts based on neutron functions: fast neutrons, thermal neutrons, and target station design. Additionally, we have accompanying engineering design and scientific research team members. NARI's neutron science facility is based on a 70 MeV cyclotron that accelerates protons to collide with a neutron target. Currently, we are planning for both fast neutron and thermal neutron targets. The diagram shows the geometric layout of the thermal neutron science station. The neutrons generated from the thermal neutron target will be utilized by the thermal neutron science station. The green framed area represents the neutron diffraction instrument, while the cyclotron and thermal neutron science station are currently in the construction phase. The design of the thermal neutron diffraction instrument involves both optical and engineering considerations. We selected MXTAS software for optical design and analytical calculations. MXTAS uses the Monte Carlo method to simulate neutron motion and is a versatile neutron ray tracing simulation software package for performing high-complexity Monte Carlo simulations of neutron scattering instruments. It provides accurate estimates of flux, resolution, parameter optimization, and design, particularly in cases where analytical calculations are not feasible. The right side of the presentation displays the user interface of the input files designed in MXTAS. This interface allows for the adjustment of 16 parameters, including neutron intensity, neutron wavelength at the sample stage, monochromator lattice distance, focusing capabilities, and parameters related to collimators and samples. The numbers displayed in the interface represent the system's default values for design purposes, serving as a reference for optimization analysis. The neutron source settings in MXTAS are based on neutron source information obtained from MCNP software. The MCNP simulation work was conducted by senior engineer Deng Yonghong. In the process, the blue bars represent the simulation results from MCNP, while the orange curve depicts the Maxwell-Boltzmann distribution at 300K. From the figure above, it is evident that these two datasets exhibit a good fit. Therefore, we will use the Maxwell-Boltzmann distribution curve at 300K as the neutron energy distribution in MXTAS. The total neutron intensity integral results will be determined by the MCNP simulation results. The figure shows the geometric modeling based on the MXTAS software with key components labeled. The positions marked by blue circles correspond to the horizontal positions of these components in the model, and the numbers within the circles match the component summary above. Since the neutron guide is only 7 meters long, the effects of gravity on the neutrons are neglected. To increase the flux of thermal neutrons, the guide is equipped with a supermirror with an M value of 3. Two options are available for the monochromator, HOPG02 and G115, and the corresponding simulation results will be summarized in tables in the following slides. The figure shows the output from MXTAS simulations. In addition to outputting data from various neutron monitors and detectors, MXTAS also generates value files for each monitor, enabling users to perform further data processing. The 6 small plots from top left to bottom right are as follows: neutron energy spectrum at the guide entrance, neutron energy spectrum at the guide exit, neutron energy spectrum at the sample stage, 2D neutron monitor results at the sample stage, 1D neutron detector results for silver powder diffraction, and 2D neutron detector spatial distribution of neutrons. The table shows the total flux and resolution for the neutron diffractometers currently designed by NARI. It includes 3 takeoff angles and 2 single crystal designs for the monochromators. The red box indicates the maximum neutron flux at the sample stage and the optimal resolution for diffraction results. Different single crystals and flight angle configurations can be used to initially assess samples using the high flux mode, followed by further analysis of specific diffraction angle positions of interest using the high resolution mode. In addition to simulating the neutron diffractometer under design, we have also developed a theoretical calculation program to cross-verify the simulation results. This program is based on the theoretical framework established by G. Cagliotti et al. 1958 and is implemented in Python. It allows input of relevant parameters for the collimator, monochromator, and the lattice constant of the sample being studied. With these inputs, the program provides analysis of the sample stage's relative neutron intensity and the resolution of the sample's diffraction results, along with predictions of diffraction patterns. To facilitate comparative analysis, the program allows for the output of diffraction curves in different colors under varied input conditions, with overlay capabilities for direct visual comparison. Additionally, a neutron intensity weighting parameter is incorporated to address the theoretical limitation of calculating only relative neutron intensity, enhancing its utility for comparison with simulation outcomes. The current version supports theoretical diffraction predictions for FCC, user mode, and BCC, developer mode crystal structures. To ensure rigor, we perform dual verification of theoretical calculations and simulation results. The upper image shows the results of theoretical calculations, while the lower image presents the silver powder diffraction pattern simulated using McStas. As shown, not only do the diffraction angle results from both calculation methods closely match, but the neutron intensities calculated by both methods also demonstrate a degree of consistency. This is attributed to the neutron weighting function in our self-developed program interface, which enables an analogy between the theoretical calculations and simulation results. The figure shows a resolution comparison between the theoretical calculations and McStas simulation results, with the horizontal axis representing the diffraction angle and the vertical axis representing the lattice resolution. The blue line indicates the results from theoretical calculations, while the other colors correspond to McStas simulation results under different focusing conditions. As shown, the theoretical calculations align well with the simulation results, achieving a good fit. These findings highlight that the instrument is expected to meet domestic neutron detection needs and can be applied in future studies on crystal structure analysis, magnetic materials, phase transitions, superconductivity, and other research fields. Furthermore, it has the potential to significantly enhance the training of scientific personnel. The above summarizes the latest progress in the design of the NARI neutron diffractometer. Special thanks to all the outstanding team members: Zheng Shenglong, Li Haoming, Deng Yonghong, Xu Youshin, Chen Lifang, Dong Xiaoming, Yongdun Yuan, Zheng Yiren, Chen Taicheng, Shen Tian, and project advisors, Professor Cao Zhengxi and Professor Li Wenxian. Thank you all for your attention and support. If you have any feedback or are interested in our work, please feel free to contact us or leave a comment below the video.